Hi everyone, my name is Nick Russo. Welcome to the Pluralsight Tech Skills Day 2024. This is going to be an exciting session, lots of hands-on stuff, and probably making some mistakes along the way. So let's jump right in. This session is titled Practical Python Debugging with PDB. Now this is the Python debugger that's built into Python. You don't need any fancy IDE or software to use it. It's part of the language, and I think it's relatively easy to get started with. Again, here's my name again, Nick Russo. Got my social media handle that's common on most sites, as well as my personal site if you want to learn more about me and some of the work that I've done. I suspect most of you are here to learn a new technical skill rather than learn about me, so let's kind of briefly overview what we'll cover in the next 45 minutes. I'll first cover very briefly the business scenario we're going to be addressing. Now, this is kind of based on a true story. Then we'll talk through what is our implementation plan, what are the technical things we need to do, and I'll give you a little bit of background on specific technical information you need to be able to follow this talk. And then, of course, we'll spend the vast majority of the time, probably at least 35 minutes, on the presentation. By the way, put your questions in the chat as they come up. I'll be around live to answer them because at the end of the session, we're going to kind of abruptly stop and move to the next one. So as you have questions, ask them immediately, and I will address them. Weird Brain Coffee Company. Some of you who have been watching Pluralsight for a while are already familiar with this name. Let's imagine that we do in fact have a coffee company here, and they have 3 different business goals that they want to achieve this fiscal year, let's say. They want to grow the business to new and diverse customers, and that's a key phrase there. We want to improve the diversity of the customers that are coming in, and we want to better serve some groups that may not have been served well in the past. And specifically, we want to reduce delivery errors to visually impaired or VI customers. So people who are on a spectrum of visual blindness. People come in and they get their coffee cups. If they don't hear their name called, clearly they can't see the cup, so they won't know which one is theirs by looking. There might be some errors in that, and we want to reduce it and create a better experience for those people. We also want to establish personal relationships with them, and one of the easiest ways to do that is to use someone's name and to mark something with someone's name and to refer to someone by their name. So we're going to take these basic kind of concepts and try to roll them into a new product offering. So let's get started. We have our coffee selling person, our barista. He's behind the counter, he's making cups, and here's what a standard delivery might look like. It's your coffee cup, it's got the protective sleeve on it, and someone's name written on the top. So this is kind of our template for what the product is. But in comes the visually impaired customer who can't read the name because she can't see. So what can we do in this particular situation? Well, my idea, and again, I question whether this is workable from like a manufacturing and a logistics standpoint, but let's just go with it from a computer science standpoint, is to put Braille on the protective cover. So it's that little platform or that little cardboard ring that slides on the bottom of the cup, and we would raise or punch little dots in the cardboard, and when you swipe your finger across it from left to right, you're able to read the Braille. In order to implement this from a computer perspective, we need to stick our hands in a lot of different technologies to understand this. So first we need to understand Braille at a basic level. Now, I am not going to teach you Braille. I do not expect that any of you have ever seen this before. I don't expect that you know it, and I don't expect you to know it. I just wanted to demonstrate that the level of Braille that we are going to be working with in this course is going to be what's called grade 1, which is the 26 letters of the alphabet. You can see on the right-hand side, we have a special symbol for a capital sign and a number sign. The way you can think about the capital sign is almost like the shift key on a keyboard, where you push shift first and then a letter, and it makes it a capital letter. That's exactly how it works in Braille. We have to prepend that capital sign, that symbol, before the letter, and that makes a capital. We do the same for numbers, and again, I'm not showing the number values here, but those also exist. Some of those words at the bottom, like and, the, ing, and ed, those are part of a higher grade of Braille, so we're not going to be using those, but we will map the letters and some of the other basic punctuations, and there's a reference to where I got this chart. Now, in terms of programming, we're not too worried about what the symbols are because we're not going to be reading Braille. But in terms of programming, how do we represent these individual characters? And what I find is the most common and intuitive way is to use Unicode. So these are the individual code points for all possible combinations of the 6 dot Braille characters. Now, take a minute and look at this chart. You can see that the width of the chart is 16. We know that because it goes from 0 to F, so those are hexadecimal. And then we have 4 rows from 280x to 283x. Okay, so we're basically counting by 16s in the rows. So if you think about this, from 0, 0 to 0, from 0, 0 to 3f is going to be 64. It's going to be 16 in each row times 4. That makes sense. So 2 to the 6th power, that also makes sense because we have 6 individual dots, which can either be set or unset. So just think about it from a basic binary number system perspective, the fact that there are 64 values, 2 to the 6th power. And if you look at this chart, can you see the pattern in the dots? And I'll give you a hint. If you look, I'll give you 2 hints. Look in the top left corner and then look in the bottom right corner. And what do you see along that kind of diagonal process? And another way to think about this is look at each column. What do you notice that's similar about each column? Some of you have probably seen it. It's counting in binary. So for example, let's just pick column number 7. And we can see that in column 7, the 1, 2, and 3 cells are all, or the 1, 2, and 3 dots are all raised, but the 4, 5, and 6 are not. But then as we go down the cell, you can see that some of those dots on the right start to get turned on as we increase. But you can see that everything in the 7th column has those left 3 dots on. And that's something that you'll notice within the individual columns is that there's kind of a dot that represents a base value and then more dots get turned on. And that's generally true throughout this process. Now, knowing those patterns isn't too important. I just wanted to kind of prove to you that we are going to be doing this binary counting, and that's great because that's how computers think. So by doing a little bit of bitwise logic, we'll be able to say, given this individual code point of 2801, for example, we'll be able to test all 6 of those bits, see which ones are on, and based on the ones that are on, we can plot those points, and on that plot, we'll get kind of a visual representation of what dots are supposed to be on, and then later in the process, we can send that to our manufacturing machine to make a prototype. Okay, so that's the general idea. And we're going to be using Python PDB to step through this process at a low level. And I'll be teaching you probably 10 or 15 different PDB commands to do that. So next up, we're going to jump into the demonstration. And this is where we get to do the fun stuff. All right, everyone, here we are in the demo. So I'm sharing my terminal screen here. Again, there's no fancy software. It's just a terminal. And we'll be using Vim, basic text editor, to look at some of these files. But before we jump into the files, I want to help solidify your understanding of some of the Braille and Unicode stuff we talked about before, because for some of you, all you've seen is a picture of Braille and a Unicode chart, and that's the extent of your experience. And this session is not going to be very interesting if that's all you've seen. So let's invest a little bit of time to understand this a bit better. We're just going to go into the REPL here. So here we are at our interactive shell, and we can just type Python code as we want. And the first thing I want to do is just remind you think about the ASCII integer mappings for like the alphanumeric characters. So for example, some of you may know that decimal value of 65 corresponds with capital A. And if we convert that to hexadecimal, we would get 41. So 4 times 16 is 64, plus 1 is 65 in decimal. And in Unicode, which is pretty cool, is that those first 127 characters are retained, those ASCII values are retained in Unicode as well. So the way we can represent this in Python is with a Unicode string, which by the way, string literals in Python 3 are Unicode strings, unlike in Python 2, so we got that going for us. We can begin with a \u. Now what follows is going to be our code point value, which is our 4 hexadecimal digits here. So we can say 0041. Now the zeros are just blank because these ASCII characters don't use that second byte, but that first byte is going to be the decimal value of 65, or in hex it's 41. So if we hit enter there, we can see it's just a capital A. And of course, this is just using Unicode to represent that string rather than the literal character of A. Now I'm showing you that because we're going to use this same technique in the context of Braille. So if we go back to our Braille chart, and again, I don't expect you to memorize it, but I'll just kind of narrate. The very first top left value was 2800. That's with all the bits turned off. And this is going to give us a space. So in Braille, we have this idea of the space character, which is all bits turned off. But if you can imagine, there are actually 6 little dots in there. They're just not on. So let's turn on one of them. If we change any of these values here, maybe to a 1, You can see that little dot in the upper left corner of the Braille cell. This represents the letter A in Braille. Now, unfortunately, Braille doesn't just count. It's not 1 is A, 2 is B, 3 is C. That's not how it works. There's a different kind of pattern. And that's why we're going to look at a mapping of that in a little bit. But just to get an idea, this is a good way just to practice some of those values, to look at that chart and try them. What if we turn on a second bit? So for example, 1 and 2 is dot number 2, and when we combine them, 1 plus 2 is 3. This is turning on two different dots at the same time, namely dots 1 and 2. When I edit this video, I'll put a little chart somewhere on the screen that shows what those 6 dots are, so you don't have to memorize it. But again, it's 1, 2, 3 from top to bottom on the left, and then 4, 5, 6 from top to bottom on the right. What if we want to turn on yet another bit? Let's turn on the third bit as well. So that would be adding 4 to this, because to the second power, that would be the next bit in the sequence. So we should be able to do 7 here. And now you can see how we're kind of turning on bit 1, and then bit 1 and 2, and then bit 1, 2, and 3. We can kind of continue this process if we want to turn on bit 4. Bit 4 would be 8, so 2 to the third power. 7 plus 8 is 15, which in hexadecimal is F, so 280F. See, now we have 1, 2, 3, and 4. You can see that with kind of this upside down L shape. Now, just to demonstrate the range here, if we want to turn on all the bits, we can do 3F. So again, this is 63 in decimal, and this is the maximum value, so we should see all 6 bits on here. And by the way, this is the word 4 in Braille, a shortcut for the word 4, which is very high grade. We don't need to know that, but just showing that these are all the different symbols. And of course, there are 64 combinations here. And I'm just showing you a handful so you can become a little more comfortable. Now, before we move on, also consider that every character will have an ordinal value. And this will give us that kind of integer representation of it. So for example, if we say the ordinal value of A, it gives us 65. So 0x41, the hexadecimal of 41, is the same as decimal 65, as we talked about before. Again, if you've worked with ASCII, this is not really a new thing for you. But what if we pass in some of these other values? We can say ordinal of, let's say, the maximum range, which is 283F. And I apologize for looking down here. I need to see my keyboard because this is very precise typing. We can also get the ordinal value of, let's say, 2800, which is the bottom of the range. And again, I'm just doing this as a 2-tuple so we can see both at the same time. And these are just the numeric values of basically 283F and 2800 represented as their ordinal values. Look at the difference between these two numbers. So we have 10,303 and 10,240, and the difference between them is 63. So that range from 10240, representing the space, to 10303, representing all 6 dots being on, is our range of the numeric values. So let's go an example here. I'll just say the letter N, and the letter N happens to be this. So if you look at that Unicode chart, you'll see that this is the value for the letter N. So if we assign this variable, and then we just display the value of that variable, we can see these dots here. Now, if we look closely here, look at what dots are raised and which ones are not. So 1 is raised, 2 is not, 3 is raised, 4 is raised, 5 is raised, 6 is not. Okay, so pretty much everything except 2 and 6. So what we can do here is we can take the ordinal of that value and then subtract this base value. So this 10240 is the minimum value. And if we strip that away, we're going to get a number between 0 and 63. And guess what? If we have a number between 0 and 63, that means it's between 0 and 2 to the 6th power, and then 2 to the 6 minus 1 technically. And then we're able to test the individual bits within that integer. So we get a number of 29 here. Now I'm going to use an F string here just to print out we take 29. We are going to print out the 6 positions of binary here. And what this should give us is the binary string representation of that number. So just like I said, if we read from right to left, first bit, so dot number 1 is set, dot number 2 is off, 3, 4, 5 are set, and 6 is off. So you can kind of see that everything we've been talking about fits together within this plan. Okay, so if you're not familiar with Braille and you just want to play around with Unicode and the code points and the binary a little bit, this is a good way to do that interactively without having to write any code. So I'm going to break out of that. We'll Control D. Let's list our files again. Now we're going to get into our code. I'm going to open up these 2 files. We're going to ignore the rest. We're going to focus on these 2. I'm going to open up the symbols.json mapping, and the plot.py script. So first, the symbols.json mapping, it's relatively straightforward. Now, I told you earlier that the Braille symbols don't actually follow a sequence here, at least not one that I could tell. So I can't just use a for loop and count to generate this. So I statically define this, and I show that A and B and C, these all map to the individual code points based on what the chart says. We jump down to the bottom, you can see I've also included a few other punctuations that are relevant. We'll close that file because we're probably not going to need it again. Just wanted to show you that this mapping does exist, and you can see all the different relevant code points are listed here. Now, this is the file that we're going to spend more time on. So we're going to print Braille symbols on Cartesian coordinate system, and I'll show you how that works a little bit. The main Python package we're using to actually do the plotting is matplotlib, which you can install using pip. Line 17, I declare a constant, which is that base Braille value that we can subtract. So when we have our Braille, our value, our Unicode code point, we can subtract that value from it to get a number between 0 and 63, so we can do our bitwise math on it. Jump down a little bit. This grid is going to allow us to plot the different points on the matplotlib to tell us where the points go. We can use this mapping, this dictionary, to input a Braille dot and get back a XY coordinate in the form of a two-tuple. Again, you're going to see how this fits together soon. Line 33, we're going to go through that very quickly. We just load in our JSON file, so we have it in this constant called symbols. Now in the main function, going through this briefly, you can see I have some commented out breakpoints here that we are going to activate as we play with PDB. We have a function called convert name. So main takes in a name like Nick or Joe or whatever, takes in the name. And then we are going to call a function called convert name. And what that does is it takes a string and it converts the name to Braille using our mapping. That's it. Now, when I first wrote this program, that was the extent of the work that I did because I didn't actually plot it using matplotlib. That comes later. But just converting the name to Braille, we use our dictionary, and you'll see that in just a minute. Then I use this for loop and say for each symbol in that Braille string. So we're going to kind of iterate over that string, symbol by symbol, character by character, and we're going to plot each one. Don't worry about the I and the I times 2. That'll make sense soon. Then on line 59, we do some cleanup for our graph. We give it a header, we give it a size, and a few other attributes that aren't terribly important right now. Plot symbol. This is how we plot the individual symbols. At the beginning, we do a little bit of error checking to make sure that we're tracking exactly one symbol. We do some more checking here to make sure that our parameters make sense. And again, I'm going through this extremely fast because we're going to go through it slowly with PDB. I just want you to have an overview of what the code is so it's not a complete surprise when we encounter it doing our debugging. Line 84, we do a little bit of colorized formatting, alternating characters between red and blue. Again, I'll explain that a little bit later. Line 87, this is our for loop that goes through bit by bit. So for each of the 6 bits in that character, we want to test whether they are raised or not. We do that on line 95. If it is, then we're going to reference the proper grid point and plot the point. Again, we're going to go through this in greater detail and examine the values of these different variables as we go. Convert name, this is relatively simple logic where we're going to say for every ASCII character in the person's name, first we test for uppercase. If it's uppercase, we prepend the Braille upper symbol. And then unconditionally after that, we will reference the symbols dictionary, looking for the lowercase value of the character, and then adding that to our Braille string. When that's done, we return the Braille string. Now at the very bottom, you can see that if we don't specify a command line argument, we use this default name of WB Coffee Co. You can see there's a mix of capital, lowercase letters, and spaces in this string. Or if we do specify command line arguments, we'll just strip off the first one and pass that into the main function. You can see that on line 126. Okay, so super quick overview of the code there, because I think it's more interesting to see this in action and to treat it like a troubleshooting exercise. So let's just run plot.py. And I'm going to move this window up to where you can see it. And you can see here, I'm going to scroll up a bit. My code will go and it will print out the Braille name, and you can see it in the top left corner of the terminal and on top of the graph in the picture, where it shows out WB Coffee Co. just in regular Braille as a Unicode string in Python printed to the console. That looks good. And then for every character, identify the bits that are raised. And you can see that symbol dot using format RO and BO, that's just red and blue coloring. And you can see that alternating blue color makes it a little bit easier to read. That way it's not just a big mass of black dots. And again, we're not going to focus too much on this, but this is just kind of the debug output, and we're going to see how this works soon. So if I close this window, script ends. You can see if I also put in something like Tech Skills Day, like TSD as a name, it'll do the same thing. Obviously, this is a shorter string, so there's not as much to do there, but you can see we get those 3 letters printed out in the right sequence, and this would be on our coffee cup holder. Okay, so that's the idea for what we're doing. So first, let's jump in plot.py, and I'm going to look for all the breakpoints, and I'm going to uncomment the 3 that I positioned. Now, I put them in certain places so that I could teach you certain skills. Knowing where to put a breakpoint is going to be based on the code you're trying to troubleshoot, but I've placed them in places that I think are going to be the most educational. So now if we run our code, when you use that word breakpoint, and you treat it like a function, what happens is that when that code is encountered, your program will get suspended at that particular line. So you see here in plot.py, line 49, in the main function, we are awaiting to run this line of code right here, Braille equals convert name. And that's what we're looking to run. So if you don't know what to do, if you're completely confused and you're lost and you don't know any commands, just type help. Now PDB gives you this kind of summary of all the available commands, and you notice that some commands are only 1 letter long. Those are just shortcuts for their corresponding commands. And you'll see me use a mix of long form and shortcuts in this talk, just so you can be comfortable with both. And the first command I want to teach you about is the command called list. So what does list do? Help list. We can learn about it. So I'm not going to read this whole thing to you, but if you look at the first couple sentences, it says list the source code for the current file. Without arguments, it lists 11 lines around the current line. So what that means is it'll print out the line that we're currently on, as well as 5 before and 5 after. So it kind of gives us a window into where we are right now. So if I type list, we can see that's what we see. We see line 49 is where we're at. You can see we got this little sandwich of breakpoints around it. Some code, and the nice thing is that this also shows comments. Now, even though comments and spaces aren't evaluated by PDB as runtime actions, they are still present and we can see them, and reading those comments may help us understand what's going on. There's another command that you may have noticed there called long list. So let's see what long list does. Long list will list the whole source code for the current function or frame. Now, what's useful about this, I'll show you here, just with a demonstration, we do long list, it will show the entire main function. So rather than just saying, show me in this little window, it will show kind of the entire context or the entire scope of where you are. So we're inside the main function and we can see all the code available in it. And if you have a little bit of a bigger screen, this can be a useful approach as well. If I type help again, I can also just type H, by the way. So I'll just type H as a shortcut. You can see we have these aliases called L down here and LL. You can probably guess what those do. L is like list, and it can also take in a number. So for example, we want to say, show me the 10 lines of code around line 45. We can say L45, and we can see plus or minus 5 lines from that position. The arrow in the bottom left corner represents the code we're about to run. So our position hasn't changed yet. We're just kind of looking around the environment, seeing what the code is. We can also do a range like L from line 45 to line 65. This will give us a span of these 20 lines here, and we can kind of narrow or broaden the window as we want to using that technique with list. Again, the word list works the same as L. Of course, L is less typing, so that's what we'll use here. And likewise, LL is long list. We can type LL and get the same output from long list. So get comfortable using these commands just to know your location. That's a good way to get started. There's another command called where. You can also use W for this. This prints a stack trace. So it's as if an exception was raised from your program, and it tells you your current location, and it kind of wraps you back to where you got to your current location. So probably this is best seen by an example. So again, we can type, and by the way, you see this command here, it says where, it says W, parentheses here. It's basically saying you can type W or where and get the same result. So let's type W. And we can see here, if we start at the bottom, and in Python, the most recent call is last. So in Python, the top of the stack is at the bottom of the screen. So here's where we are. We're at this Braille equals convert name line. Where is that? It's line 49 in the main function. How did we get to the main function? Oh, we got there on line 122 of plot.py. And here's the call that got us into main. The next thing I want to talk about is something called step. Now, this step here is similar to step into in other debuggers. So you can type S or step, It runs the current line, stopping at the first possible occasion. This is a fancy way of saying if you're running a function or something that has additional code behind it, it's going to step into it and allow you to fight through all the details of that function. So for example, if we suspect that our function here, so if we suspect that line 49 has an issue, we should probably step into it. So we can type S or step. Now, when we do that, you see this word call. We see the word call because we call the function. We are now at line 101 in the convert name function, and here's the function definition for it. We can type L and see our current location. Again, this is here on line 101. We are about to jump into this function here. And let's say we want to know what some of these parameters are. If we type help and P is a way of printing the value of an expression. So if you want to print something out, you can prefix it with the word P. We can say something like P name, and it will show us what that string is. Now, for most things, as long as it doesn't overlap with a PDB command, you can also just type name by itself, and that's typically common as well. So you'll see me using a mix of those two approaches in this course, but we can see that when we ran this script without any CLI arguments, it defaulted to WB Coffee Co., and that's perfectly fine. Okay, so we're in this convert name, and we're about to do this mapping to our different symbols, but let's say you forgot your symbols and you wanted to see what they were. Let's just use the standard Python globals function call and see what are the globally available functions. Now, globally available attributes. Now, this is not specific to PDB. Globals is just an accessible thing within Python that we can use. And PDB will interpret that correctly. And we can see this gives us our dictionary, mapping the attribute name to its value. And if we look a little deeper in here, you can see some of those globals that I declared, like the Braille Unicode offset here, the grid mapping, and the symbols. So let's say if we print out our symbols, because we want to zero in on them, like, okay, that's fine, and that is correct, and it does show us the dictionary mapping between the ASCII characters and their corresponding Braille cells, but it would be better if we could read this in a little bit cleaner way. Well, there's something called PP, which is pretty print. So we can use PP symbols, and we get this nice dictionary expansion here, which shows us the mappings. And it's a lot easier to read if you're trying to do troubleshooting, and if you have maybe a large dictionary or some structure that would benefit from pretty printing. So PP is for pretty print. Let's also look at another command called next. Again, you can use N for this, just like step can be S or step, N, next can be next or N. Unlike step, this is step over. Okay, so next line in the current function. So if we were back in the main function and we use next, that next would step over convert name. It would run all the code within convert name and give you the return value from it. Most of the time, if you don't suspect that the underlying code has a problem, then you can use next. So let's type next from here. And you can see, I'll do L again in case you forgot where we were. We just stepped into the function here. So we do next. And now it says Braille equals this string literal. From this perspective, let's, before we go too much further, let's do another where. And you can see our stack trace is a little bit different now because it's a little bit bigger specifically. We're now at line 104 in the convert name script and our convert name function. This is the code we're about to run. How did we get there? We got there on line 49 of the main function when we called convert name. How did we get there? Line 22 when we called the main function. So you can see the stack trace is growing. We're adding to the stack because we're going deeper and deeper into these functions that haven't returned yet. Okay, so we have this Braille. Now notice that Braille has not been defined yet. So if I type Braille, it says name error, Braille's not defined. That makes sense because we haven't actually run this code. Now if I run that code and then I say Braille now it's been defined as the empty string. Then we encounter this for loop here. So we're about to go for each character in name. So we can see what name is. All right, so name is WB Coffee Co. So if I type N to go into the for loop, this new thing character is going to be defined as well. And what's the first character of WB Coffee Co? It's that capital W. Next, we have this code that wants to say if character is uppercase. Let's say you couldn't tell if this was an uppercase or a lowercase w. Rather than type this out, a technique I use is just copy paste the code. Just say, hey, is char.upper, is that true? Yes, it is. That means that this if statement should be true. So if I type next into it, now I'm inside the if statement, the conditional was true, and I'm going to append the symbols sub upper to Braille. What is symbols sub upper? I forgot. Well, let's just do like this. And it gives us that bottom right dot, which is kind of like that shift key that tells us we have an uppercase character coming. So let's just type N. After this, Braille should have that first character in it. Now what we're going to do is add in the actual character dot lower, which is going to be the lowercase w. So if we do a lookup on symbols char dot lower, that's the symbol for W. When we type N, Braille is now going to have that value. And now this is a capital W in Braille. So congratulations, we've written our first character. Now this process is going to repeat. Again, I'll do a quick LL just to show you the code again. We loop over each character, we test for uppercase. If it's uppercase, we prepend the uppercase marker, and then we reference the dictionary based on the lowercase value of the character and append that to the Braille string. And we just continue this process. And remember that we do have a Braille space character, so the spaces in our string are going to be automatically handled by this mapping. We don't need any special logic for spaces or punctuation because our mapping included all those values. I'm not going to go through this 20 more times. I think you get the idea. So what we can do instead is learn about a new command called continue. So continue has a couple aliases. It can be C, it can be cont, C-O-N-T, or it can be the word continue. This will continue execution, stopping when the next breakpoint is encountered, or of course if the program is over. So if I type continue, it takes us to our next breakpoint. And in case you don't know where that is, line 51 in the main function. PDB is very verbose about your location, so you know exactly where you are. We can do a quick L here to list our location. You can see that we just hit breakpoint on line 50, and now we're on this line here. And by the way, this is the walrus operator introduced in Python 3.8, which allows us to do a concurrent assignment and also return the value from that assignment. It's kind of useful in this context where I'm assigning a variable called header and also printing out the name in Braille at the same time. So we can type Braille here. We can see our full Braille string. We can type N to do that print. And that print code is actually coalesced with our PDB output. So this is standard output right here, printed from our code, shows us that conversion. And now the fun part starts where we go into the for loop to do the raising of the individual bits. So let's step into this for loop and let's just quickly print out I and symbol. So I is just a counter. Enumerate allows us to take an iterable and then count from 0 till n-1 every time in the loop, so we don't need to have an explicit counter. This is useful because by counting the characters, we're going to use this as an X offset. Because remember, if we're plotting points on a Cartesian coordinate system and we want to write the characters from left to right, which is how we read in English, we want to start at position 0 and then move our X as we write along that y-axis. That doesn't change. Okay, so that's why we have I. It gives us access to that X offset. And then we have our symbol, which is that uppercase marker. So that's how we begin here. Where are we? We are here in plot symbol. So do you think we should walk into plot symbol or should we just step over it? I think we should step into it because we want to see how it works. So let's type S for step. We'll step into it. Function call. Okay, that's an indication that you're stepping. We are in line 66 of plot.py module in the plot symbol function. We can do a where here just for fun. Again, I won't read every line of this as usual, but clearly we can see we are in the plot symbol function and we got there in the main function from here. That's where we just came from. Here we are in plot symbol. And if we step into the function, there's kind of an interesting thing we can do here that I didn't talk about earlier because I wanted to save it for a time when I think it'd be more interesting, but there's another thing called args. Args, or A, prints the argument list of the current function. That's pretty intuitive. So if we type args or A, you can see that it shows us symbol equals that Braille character and the X offset is currently 0. So rather than having to do all that individually, you can type A and see, okay, on this iteration of the function call, what was passed in, especially if you're calling a function within a for loop like we are, this can be really useful to see, okay, each time, how do the arguments change? Okay, so first we're going to test, is the length of the symbol not equal to 1? Because that would be an error. If we measure the length of symbol, it should be 1, and it is. Remember, we're trying to do this symbol by symbol, so this is just a verification to ensure that we're passing in individual symbols. Now look at line 76 and 77 here. We want to ensure that X offset is an integer and that it's greater than or equal to 0. So my logic here is the negative testing. So if it's not an integer or it's less than 0, we're going to raise an error that says X must be a positive integer. This is just additional error checking. And the reason I include it is because lines like this, if you're new to Python, it's a lot of words, it's kind of long, there's Boolean logic. What you can do is just break it down. Say, okay, let's test the first condition. It says, is instance x offset int? So x offset is an instance of integer, so when we do not, it ends up as false, which in this case is good. We want this conditional to evaluate the false. But now we also need to test this and make sure that, okay, it is an integer, but is it also positive? And this answer says, yes, it's not less than 0, so it's 0 or greater, so that if statement should be false and we should get no error. Let's get past that. Now we're at this format. Now this is going to look really confusing. Now, if you read the comment, it'll make sense, but I don't want to read a whole paragraph to you. What I showed you earlier is that I like to alternate red and blue when I print Braille because I'm not very good at it. And sometimes I can't tell where one character starts and the other one begins just by looking. So it's a little more convenient for me just to do alternating colors as someone who can see colors because it makes it stand out. So when we do our X offset, we're going to be counting by twos. So 0, 2, 4, etc. That's because every Braille character is 2 dots wide. So as we're plotting on our graph, the bottom left corner is going to be at column 0, and then 2, and then 4, and we're going to count by twos because that's the size of each block that we're printing. So what we're going to do here is I'm going to say x offset modulus 4. So this is going to give us a remainder of either 0 or 2, if you think about it. If we count by twos, 0 modulus 4, 0. 2 modulus 4 is 2, 4 modulus 4 is 0, 6 modulus 4 is 2, etc. So we're going to get an alternate there. We're going to do floor division by 2, basically just dividing by 2 to give us an integer in response. And that integer is going to be 0 or 1. That's going to allow us to get either R or B from this RB string. That's going to be red or blue color. And then we add the O onto it, which is just showing us the kind of dot, giving us that nice fat circle that we want. So if that was confusing, let's break it down into parts. So we can type x offset modulus 4 and do that 2 on it. So you can see here that x offset is currently 0. So 0 modulus 4 is 0, and then divided by 2 is still 0. But if we have a number like 2, and then 4, and then 6, kind of like what I said verbally, every time in the loop this will alternate. And 0 is going to index the first element of this string, which is R, and 1 is going to get the second one, which is blue. So we're going to get red, blue, red, blue, red, blue for the whole length of our string. And if we can test that, just by going back to our initial thing, you can use up arrow here. And I'm going to say, let's say RB, and then index all that, and it gives us the R. And if we go in here and I change this to a 2, it should give us blue. That'll be the next time in the loop. Okay, so you can spend as much time as you need to make sure you completely understand the logic and do this kind of interactive experimentation with PDB. And that, to me, is one of the biggest benefits. So now that we know this format, we'll just kind of next our way through it. Now you can see here that this print statement is going to say, print this symbol is using format RO, so this should be red in our output. And that's the reason I print it out, is just so we can see what's going on. Now we're going to step into this for loop. This for loop is going to count from 0 to 6. So for I in range 6, so if we jump into this for loop and we say I is going to be 0 the first time around. 2 to the 0 power, anything to the 0 power is 1. So after we run this bit equals 2 to the I, we're going to end up with bit. Bit is going to be equal to 1. And now we have kind of the main part of our test here, where we are saying we want to test whether that specific symbol, which again is this Braille character, we take the ordinal value of that symbol and we subtract it, or we subtract the Braille offset from it, and we get this number of 32. Remember, it's from 0 to 63, so this is a valid result. And we are doing bitwise and against bit. We can see that this evaluates to 0, which means that the if statement is going to be false. That means that this particular symbol does not have the first bit raised. And that is right. It only has that last bit raised in the bottom right corner. So if we type N, the for loop starts again. This time I is 1. We type N. Bit is now going to be 2, because 2 to the 1, 2 to the first power is 2. Our ordinal, that ordinal minus offset hasn't changed. That's still 32. But if we say 32 and bit, it's still 0, because 32 only raises that one, 2 to the 5th power. So it's that last bit is the only thing that gets raised. Okay, so rather than go through all 6 of these iterations, you'll notice that I put a breakpoint inside the if statement. So that breakpoint will trigger when it's finally true. Let's type C to continue into it. We can see now we are inside on line 97, inside that if statement. That means that our bit is a value that is correct here. So if we say 32 and bit, it's going to give us 32 because we have a non-zero value indicating that the bit is set. So now we need to plot this point. Again, let's take a look at our grid one more time. This is our mapping on the Cartesian coordinate system of where the individual Braille dots need to be. I is 5 because this is, range from 0 to 6, so this is the last value. I plus 1 is 6, so if we say grid sub 6, it's going to say at position 2, 1 is where I should draw this particular item. Now, if we type n there, you'll say dot is going to be equal to that 2 tuple. That's our current position. And under plt.plot, this is where it's going to be drawn. Now, keep in mind that our x offset needs to change, and that's why we have that when we call this function, we pass in different offsets so that when we write the characters, we don't just keep overwriting in the same location. So the x offset changes, but the y doesn't because we're writing along an x-axis, so y value doesn't change. That's why it just says dot sub 1 here, so that y value remains the same, but the x value gets offset by the x offset, which again, args, is currently 0. So we're writing at the beginning of the page, but we're going to make our way to the right. And then, of course, we have our format, which is RO. You should remember that. Okay, so I can type N here. That plots our point. And now we have this print statement, which is going to give us this output, which is convenient. So it raises bit 5, which is decimal 32, and uses this dot. Now sorry about that. That output is just something that helps me troubleshoot a bit. I'm just going to continue out of it. And you can see that now we're in another iteration of the loop. You can see it's this symbol now. Okay, so I think you get the idea here. We're not going to keep stepping through all these examples. This dot, there's a specific location for it. If we look at our args, you can see that our symbol had changed. This is the next character in the symbol in the list, or in the string, I should say. And then we also have our x offset of 2. And I'm just going to break out of this, and you can use Control D to do that. And there are other ways as well that I'll show you later, but we can break out here, and then our process is over. All right, with that complete, I want to take a couple detours and show you a couple other cool things about PDB. So first, let's do a git diff here, and you can see that the only differences that I made in this file was uncommenting those breakpoints. So I'm just going to do a quick git restore to re-comment those breakpoints so that they're out of our code now. Okay, so we have regular Python code, there's no breakpoints in it, and let's say we still want to use PDB with this file, but we don't necessarily want to change the code. Well, we can do that. We can actually run our code and say python-m PDB. So we call this PDB module and then plot.py. Now, when this starts we're going to be right at the top of the file here. Okay, so at the first executable line, which is this technically a multi-line string definition, but it's really our documentation. When we start here, what we can use is the break command. So if we say help break, without argument, list all breaks. Or if we specify a line number, we can set breaks in a certain file with a certain condition. So we're not going to get too complicated here, but I do want to demonstrate how we can add breakpoints dynamically rather than having to go into our code ahead of time and make edits, because you can't make those edits once the code is running. So this might give you a little more flexibility, although it does take a little bit of time to set up. So what we can do here is we can say break or B. We don't have any breakpoints set. If we type L of 50, let's list around our area of interest. And let's say that you're looking at this code and you're like, yeah, I want to add a breakpoint on line 48 where it used to be. So we can type break, plot.py:48, and that doesn't work. Because remember, PDB is only concerned about things that have runtime influence, so not blanks or comments. If you want to put a breakpoint, put it on the line of code that you want us to spend right before. So really, this should be a 49. Now, if we look at, it says here, our breakpoint 1 added at this location. If we type B, we can see that breakpoint 1 is on plot line 49. And if we do our L50 again, we can see line 49 has this B that indicates the presence of a breakpoint. So now if we were to continue down to it, we would stop there and we would be in the same situation we were half an hour ago when we started. Okay, we can also add another breakpoint. Let's do this the quick way. We don't need to specify the module because it'll assume we're in this particular file if we're doing it here. We can type B51, And we'll also have a breakpoint here on this print line. So we can type B51. We can do our list. We can see that second breakpoint. We can also type B or break by itself to see those different breakpoints at the same time. Now, if you're done with a breakpoint or you decided that you added it wrong and you don't necessarily want it, we can disable it. So help disable says disable the breakpoints, and you can specify a list of breakpoints to disable. Let's assume that we want to disable breakpoint 2. We can say disable number 2. If we type break, you'll see that it is in the display, but it is not enabled. So if we type L50, you can see that it's shown there, and it's something we could re-enable. So it indicates that this is a line of interest, but we're not actually going to activate that breakpoint. If you want to completely remove the breakpoint, maybe that's just a complete error, we can use clear for that. The clear command, again, can be abbreviated by CL, and you can specify the breakpoints you want to delete. So if we say clear 2, it says breakpoint 2 is deleted. If we type B, we can see there's only one breakpoint left. We type L50 for list. Now there's only that one breakpoint there. So if I type C down to continue, we're going to run all the code up until we get to line 49. Now if I type L, this is our current location. Remember that little pointer is our current spot. We hit the breakpoint, and now we're at this function. Now if we type name, what is our name? It's this WB Coffee Company. We already stepped into this, so maybe this time let's try typing next or N. We can type next, and you'll see this time runs the code without us having to go into it. And now we should have a value for Braille. And you can see how the process goes. And now we go back into our program like usual. Again, don't forget about long list. It's a good command as well. You can see all of our breakpoints within that function. And from here, we can continue to troubleshoot. Take another detour. If you are using PDB and you have an overload between a PDB command like next and the actual next function that you use to get the next element from an iterator or a generator, what do we do in that case? So let's do a quick test here. Let's define an iterator, and I'll call it, we'll count from 0 to 2, so 0, 1, and 2. Make this thing called an iterator. We can check the type of it. The type is a range iterator. That looks okay. But if I type next IT, watch what happens. So we're currently on line 55 here. If I type next IT, it moves us to line 56. It treats it like the next command. That's not what we wanted. We wanted to do next on the iterator. How can we get around this? Just prepend an exclamation mark. And that tells PDB, don't expand the PDB command, just run it like it would regular Python code. And if we do this, you can see our iterator works as usual. And the same is true for generators. And we'll just quickly do a generator just to prove it. So that being said, let's do a quick wrap up here. Help. This is your best friend. Never forget help. You can look at all the commands that are available and you can see what the individual commands do. Again, we talked about several of these commands. We talked about args, break, clear, continue, list, long list, next, P, PP for print and pretty print. Quit, we'll talk about that in about 2 seconds. Actually, we'll just do it now. You can just quit. Or Q is another graceful way to exit PDB instead of Control D. We also talked about step versus next. Remember, step is step into, next is step over. Those will be common things that you use. And also the where, which prints out the stack trace and gives you some idea about your current location.